Okay, so time to talk about fundamental theorem calculus number 2, or FTC number 2. If f is continuous on an open interval I containing a, then for every x in the interval, this is going to be something that holds true. So the derivative of the integral from a to x of f of t dt is equal to f of x. Okay. This is what I call the liar theorem. I really enjoy talking about this theorem because I feel like it's trying to gaslight you into thinking that it is easier than it really is. And it is easy, but there's also like more to it. So let's talk about what's going on here. So the things that I think that they are a little bit not backhandedly not showing you. So we have d over dx of the integral from a to x f of t dt. So when we're looking at this, we need to be a little bit careful because you may look at this and go, oh, well, the integral and derivative cancel each other out, and then that's it. So it's just that function. And it is true in this case. So let's talk about what would happen. So if we were to do the integral, we would have FTC number 1, we take the integral, and then we plug in our interval top minus bottom. We'd be done. But we're also taking the derivative now. So we're going back to the original function, and we need to be careful about any chain rule that might have happened. We're plugging in this interval, so we have to worry about that inside function. So when we do this, we get f of x minus f of a, which is that integral piece that we would have had. And then we're also going to multiply by the derivative of the inside. The inside in this case is x, so we're going to take the derivative of x. And the inside in this case is a, so we have the derivative of a. And then we're going to do some simplifying. Because that's what ends up happening is we end up simplifying things, and that's why we get the equations we get later on. So we have f of x times the derivative of x is 1 minus f of a times the derivative of a. Well, the derivative of a is going to be 0 because a is something in that interval, which means it's a number. So if I were to simplify what I have here, f of a times 0 is going to go away. We subtract 0. We don't need to write it. F of x times 1 is just f of x, so I don't need to write 1. So looking at this, yeah, we got the exact same thing, but there is more to it than just what we have here. And that really comes up when we look at things like this. So if I need to do something with this integral, I don't really want to take the derivative of the integral of tangent of t. And so we are going to kind of look at what we got going on. So if we were to do what we just did, we have our original function, tangent of x, but we need to plug in that interval. So I'm going to plug in that x squared, and then we're going to subtract tangent of x, but with our other interval plugged in. So I have tangent of negative x. Now we're going to go ahead and do the derivatives of both things, but we want to do the derivatives of the insides. So I have d over dx of x squared, and we have the derivative of negative x. So we're going to go ahead and simplify what we can. So we have tangent of x squared. Oh my gosh. Tangent of x squared times the derivative of x squared, which is 2x. We have minus tangent of negative x times the derivative of negative x, which is negative 1. And then I might simplify it just a little bit more to make it look nicer. To get this. But if I were to do it the way that it looks in this formula, I would probably just say that this is tangent of x squared. And these are not the same thing. These two things are not the same. So this is why that I call this kind of the liar theorem. It's gaslighting you into thinking it's easier than it is, even though like it is not like the worst thing ever. It just, there's more to it. So not quite the same. So just like there is Taylor's version, we have Melchor's version. So mine's going to look less mathematical, but the big things that we need to know is that if we see the derivative of an integral, and we have some sort of interval here, if it's just numbers, if we take the derivative of an integral, it's going to be fine, it's going to go away. But if it's literally anything else, we need to think about it a little bit more. So we have f of the top times the derivative of the top minus f of the bottom times the derivative of the bottom. So you just really need to make sure that you think about what we're doing, why we're doing it. They do cancel each other out as an integral and a derivative, but there's a little bit more that goes on with it because of how derivatives and integrals interact with each other.